Welcome to episode 3. Definition 3.1 states, let f be a differentiable real-valued function on R3, and let v sub p be a tangent vector to R3. Then the number v sub p of f equals the derivative, set equal to the derivative of f of this point p plus t v, then evaluated at t equals 0, is called the derivative of f with respect to the tangent vector v sub p. So just to keep track, here we have this function evaluated at some point which depends on t. Then we compute the derivative with respect to t of whatever function of t we obtain from f. And then after computing the derivative, we set the parameter t equal to 0. Let's consider an example. Suppose f is equal to x squared plus yz plus 5. And then we'll choose points 1, 1, 1 for p, and negative 1, negative 2, negative 3 for v. Then the line p plus t v is simply equal to 1 minus t, 1 minus 2t, 1 minus 3t. Let's use the figure just to follow along. We will consider p and v as points in the xy plane, just for visualization, although these are in 3 coordinates. These are points in the xy plane, and the line p plus tv contains all the points which start at p and then continue for some distance in the direction of v. So here's p, and then we add v, we get another point on the line, and then the line in the xy plane, which contains both p and v extending off like this, is the line that we have with parameter t to give us the different points along that line. Then we can consider f of p plus tv, which is the value of the function f evaluated at the points along this line. So here we have this surface which represents the values of f. The height of the surface above a point p gives the value of f at p. So here's f of p right here, and here's f of p plus v, another point above the line, p plus tv. And then we obtain some curve along the surface, which represents f of p plus tv for all the different values of t. So plugging in the different values, 1 minus t for x, 1 minus 2t for y, 1 minus 3t for z, we obtain this polynomial in t. We simplify, and we find that it's simply 7 times the polynomial t squared minus t plus 1. Then the directional derivative of f with respect to the tangent vector v sub p is by definition the derivative with respect to t of this quantity f of p plus tv, and then the derivative of that evaluated at t equals 0. So we plug in our polynomial, we compute the derivative, 14t minus 7, and evaluating at t equals 0, we get negative 7 for our directional derivative. Now, given a function f on R3, f has 3 arguments. That is, we may write partial f partial xi with meaning. So recall in Calc 3, we might have a function f of x, y, and z. Then we could say, what is the derivative of f with respect to x, holding y and z constant? That makes sense when we just take a function on R3. However, the object f of p plus tv is not a function of 3 variables. Here, f is being evaluated at a point, and that point is a function of 1 variable t. So suppose we just chose a particular value of t, say 7. So we have a point p plus 7v, and then we evaluate f at that point, then that gives us a number. And it doesn't make sense to take the derivative of a number, right? Instead, we're saying, okay, whatever this point is, it's depending on this parameter t. So instead of getting just a number, well, it is a number, but it's undetermined, and it depends on this variable t. And so in this sense, we're allowed to take the derivative with respect to t of this object. So the partial derivative with respect to one of the standard Euclidean coordinates xi of this object doesn't have meaning, but the standard derivative with respect to t of this object does have meaning. We can look in the figure and recognize that these both the partial derivatives that we're used to and the directional derivative is defined above have a similar interpretation, but we're going to generally avoid using this notation like partial f, partial y, and instead prefer the more general notation for directional derivatives so that we don't get confused with these types of derivatives that we're using. So this is a classic Calc 1 derivative, but this entire quantity is what we're calling a directional derivative, or just the derivative of these multivariable functions in this new setting. Lemma 3.2. This lemma states, if we write a tangent vector, v1, v2, v3, applied to the point P, and we say this is a tangent vector to R3, of course, then we have the following formula for the directional derivative of f in the direction of v applied to the point P. The formula is somewhat reminiscent of the chain rule. So let us derive this formula. Just to interpret what this lemma is saying, it says, given a function f on R3, the directional derivative of f at P in the direction of v is equal to the derivative function of f in the direction of v evaluated at P. Okay, so we have the derivative of f at a point, and then we also have a derivative function. The derivative function is simply the function which returns the value of the derivative at any given point. So it's a matter of which order we are evaluating. We could first find a point in our direction and then evaluate the derivative at that point, or we could define a function which will give us the derivative of f at any point we like, P. So similarly above, we could say, here is the notation for the derivative of f applied to a particular point, and then here is the derivative function, right, these partial derivatives, which are functions, and then we evaluate those functions at the point. So the order is slightly off. In order to prove that this equation makes sense, we'll write P plus T times V in coordinates. So here we have the Pi plus TVI, where Pi are real numbers and the Vi are the Euclidean coordinate functions. Then, of course, this derivative of f of P plus TV could be written in coordinates as well. We compare this to the following sum, which resembles the chain rule. We have partial derivatives of f, followed by derivatives of the points at which f is being evaluated. and then we'll take this sum and evaluate it at t equals 0. So we follow this whole relationship in the schematic to the right. We're starting with a function f, which takes points in R3 and maps them to real numbers. Firstly, we will evaluate the point, the function f, at an unknown point. We'll just write it as x1 of t, x2 of t, x3 of t. So these are each different functions of t. Now, using the chain rule, we can take the derivative of f with respect to t, and in order to compute this derivative, we will first take the partial derivative of f with respect to the arguments, so x1, x2, x3, those are the arguments, and then after taking the derivative of f with respect to, say, x1, then we have to follow up with the derivative of the inside function x1 with respect to t. And we do this for 1, 2, and 3, and we compute the sum. Then we will say for each of the xi what we want xi to be. So xi of t is equal to pi plus t vi. That's our choice for xi. So replacing each of the occurrences of xi with this, we will find that this derivative of xi with respect to t is just going to be vi in each case. From there, we have taken the derivative of f with respect to t, and then we've decided what the xi's are. And so this amounts to simply the derivative with respect to t of f of our point p plus tv. So that's what we were starting with, and we came to this end point by the chain rule first, and then evaluating. We could have otherwise simply just evaluated at p plus tv, and then we end up with the derivative by taking the derivative of whatever this function of t is. But this direction doesn't really show you what's going on. Going this way is a little bit more explicit, and that's the manner in which we obtain this expression here. Then we simply take this expression and evaluate it at t equals 0, and that's the same as taking this expression, evaluating at 0. Now for theorem 3.3. We will let f and g be functions on R3. Then v sub p and w sub p be tangent vectors, and a and b be real numbers. Then we obtain 3 different useful facts. The first 2 are facts of linearity. We have linearity of the directional derivative in tangent vectors, and we have linearity of the directional derivative in the functions we are differentiating. And then the third is our analog to the product rule. We refer to lemma 3.2, which gives us this formula for the directional derivative. Firstly, let's consider the linearity of the directional derivative in tangent vectors. Using our formula, we immediately replace vi with avi plus bwi, which are the coordinates, the components of the vector a v sub p plus b w sub p. Then we distribute, so we take the partial derivative of f, and we distribute across the sum to obtain this sum. We then group the terms so that we have the vi's and the wi's separated. And then we factor out a and b respectively from these groups. And within the parentheses, we have the exact form for the directional derivative. And so we rewrite our equation and conclude the proof for part 1. For part 2, we use again the formula, replacing f with af plus bg, since that's the function that we are differentiating. And then, since this is just a partial derivative, it's nothing fancy, and it doesn't require our knowledge of vectors and points, etc., we can simply use the linearity of the derivative inside our formula. So we do that here. Then we distribute vi across the sum. We factor out a's and b's, and then we group. And by grouping, we obtain in parentheses again the formula for the directional derivatives. And so that gives us the formula for part 2. For part 3, we again use the definition. We replace f with f times g. We again use the fact that this is just a partial derivative inside here, so we can just use the product rule for partial derivatives. And then we distribute again, and we group. We use the fact that the product of a function, the product of functions evaluated at a point, is the product of the values of those functions evaluated at that point. So here, partial f, partial xi times g evaluated at a point is just the product of partial f, partial xi evaluated at the point times g of evaluated at the point. We do that again over here for f and partial g, partial xi. Then g of p is constant. It doesn't depend on the index I, so we can factor g of p out of the first sum, and then we can factor out f of p out of the second sum for the same reason, and thus we obtain our product rule for directional derivatives. All right, we need the following definition. Given a vector field v and a real valued function f, the operation v of f returns the function whose value at each point p is v of p of f. Let's break that down. The vector field does to a function what it does to a point, but it does to the function this operation before the function is evaluated. So we can take a function and we can take a vector field and we could say the resulting function v of f is simply the function which returns the directional derivative of f in the direction of v of p for each point p. We also make a notational note. So the notational difference between v of p of f, which is the derivative of f in the direction of v of p applied at the point p, and v of f of p, which is the function v of f resulting from applying v to f, then applied to the point p, is not substantial. This notational difference, v of p of f and v of f of p, is not substantial. These are always of equal value. So whether we first compute the function v of f and then apply it to a point, or we apply the vector field to a point and then compute the directional derivative, we will obtain the same thing. Corollary 3.4 states that if V and W are vector fields on R3, and F, G, and H are real-valued functions, then we have, again, the linearity structure that we saw in Theorem 3.3. And we also see the product rule structure that we saw in Theorem 3.3. So here, instead of real numbers, you could think of these functions as being our scalars. And so now when we apply a vector field, a linear combination of vector fields with scalars, these real-valued functions, we obtain the same thing as just a linear combination of the vector fields being applied to our function. Likewise, the application of a vector field to a linear combination of functions gives us a linear combination of these functions. And the application of a vector field to a product also obeys this product rule structure. So we'll just briefly prove these, making use of Theorem 3.3. Firstly, the value of the operation of this linear combination of vector fields FV plus GW on H at some given point P is written this way. We take the vector field, we apply it at P, and then we compute the directional derivative of H with respect to that vector, since that's the definition of the vector field operation. Then we use Theorem 3.3 to rewrite this vector F times V plus G times W of P as follows. We simply use the linearity. Then we use the notational equivalence of V of P of H and V of H of P, and likewise W of P of H and W of H of P. We swap those around. That's our next line. Then we say, this expression right here, these products of functions evaluated at P, that's simply by definition the same thing as taking this one big function and applying it to the point P. We use the fact that the linear combination of functions is a function. When we apply that, we evaluate that at the point P. That gives us the same thing as the linear combination of each of those functions evaluated at the point P. Next, we consider the value of the vector field V operating on the linear combination of functions AF plus BG, then evaluated at the point P. This is the same as first using the vector field and applying it to the point P, and then computing the directional derivative. But then we use the linearity of the directional derivative from Theorem 3.3 to obtain the next line. We use the notational equivalence of this V of P of F and V of F of P to rewrite the next line. And then we use the fact that this linear combination of functions applied to P is the same as the linear combination of the functions each applied at P. So this is, again, a definition rule. finally, we check our product rule. So again, the value of our vector field applied operating on a product of functions f of g evaluated at the point P is written like this. But this is a directional derivative. We use theorem 3.3 to rewrite using our product rule version of the directional derivative. Then we use the notational equivalence to rewrite the product rule, and then we rewrite this as just one big function being evaluated at P.